should know in this EMT covariance. Okay, and just so things that you have heard and probably you have done in your even in your undergrad classes, that when you learn your Lorentz transformation, you apply your Lorentz transformation to Maxwell's equation, and you see that the Maxwell's equations are valid, have the same form in both frames, one which is at rest and one which is moving at a speed v, right? So this is something that you have seen before. This is exactly what I have written. And in the next class, I'm going to do the reverse, which is much more interesting, new. But today, let's start over here. So Maxwell's equations are valid in all Lorentz trains. This is what you know. Now, one thing that you should remember over there, that in this statement, this speed of light and q are two parameters which are entering these equations, right? And for this Maxwell's equation to be Lorentz invariant, these two parameters, the q and the c, these two should, be should be Lorentz scalars. Okay. Now c, of course, is invariant by postulate. Lorentz scalars mean it doesn't change from one frame to the other, and the q is an invariant by an empirical fact. So we know that charge in one frame is same as the particle carries a charge in one frame, which has the same charge in another frame. So that's an empirical factor. However, if you look at the charge density, then I can write down the charge density like this, where dq is rho times this three coordinate differences, dx1, dx2, dx3. So that gives the volume, and that is invariant. Okay, so dq is invariant because that's, as I said, is the empirical fact. Now the four volume, dx0, dx1, dx2, dx3, that is also invariant. So this is a homework that you should do. Okay, it's very simple. This is invariant, okay, because you see the Jacobian of transformation between one frame to the other, that actually the determinant of that transformation, lambda, okay, that is unity. So if you transform between one four volume to the other four volume, it becomes invariant. Okay, so if that is invariant, then your rho must transform as the zeroth component of the fourth vector. Okay, because if you compare these two, dq is the invariant, where it's rho times dx d1 dx d3, and then the four volume, which is dx0, dx1, dx2, dx3, that is also invariant. So your rho, that should transform as like dx0, right? So rho should transform the zeroth component of the four vector. That is something. Now, knowing that, you can write down this continuity equation in the tensor form. Okay, and in the notes that I put up, I told you, or it was written, how to write down derivatives in the tensor form, the terms in the term of this colon. Okay, so j mu colon mu with the gap. So the second mu is written with a gap. It means that j mu is taken, the derivative of j mu is taken with respect to mu. Okay, that's the thing. So over here, the zeroth term is this del rho del t, and the 3xyz term is this divergence of j. So these two terms can basically be written in one tensor form. Okay, so you can write down j nu colon mu, that is equal to 0. If you define suitably the j mu as your rho c by j, if you define it like that, then we have this tensor form. Okay, over here, this was the current equation, so this can be called the forecurrent. Okay. In a couple of classes later, we are going to do in some detail the different gauges in EM theory. So there are, other than the gauge that we used last time when we talked about charge conservation and stuff like that. There are other places where we use terms called gauge. And the two gauges that comes very often in EM theory are one which is called Coulomb gauge and the other which is called Lorentz gauge. Okay. Now, Coulomb gauge is putting a restriction which is divergence of A is equal to 0. So having a certain restriction on the vector potential, divergence of A equal to 0. When you do that, that is called a Coulomb gauge. And you can put that restriction, and that simplifies certain equations, basically wave equations of the potentials. And one can see what happens when you have the Coulomb gauge. Similarly, there is something called the Lorentz gauge, okay, where divergence of A is not equal to 0, but divergence of A plus 1 by C del phi del T is equal to 0. So it's a connection between the vector potential and the scalar potential. So divergence of A, okay, plus 1 by C del phi del T equal to 0. That is called a Lorentz gauge. And once we have this kind of gauges, then certain equations get very simplified forms. In fact, if I have a Lorentz gauge, which I said, okay, so over here I said a previous lecture, but it's not be a previous lecture, it will be a future lecture. Then you will see that if I put this Lorentz gauge, which was divergence of A plus 1 by C del phi del T equal to 0, then the wave equation that we get in EM separates out into two wave equations. One which is for the current and another which is for the charge. So the current wave equation is given by the first one over here, which is the divergence squared A, Laplace squared A minus 1 by C squared del 2A del T2 is minus 4 pi C by J. That's like the wave equation, right? But that is for the current. And then there is the one for the charge. So one wave equation which involves the vector potential and another wave equation which involves the scalar potential. So we get two separate wave equations. So the vector potential and scalar potential are separated out due to this Lorentz gauge. Okay. Now, over here, remember we have written charge and the current together as J mu, like this. So in the same form, we can couple this side. So this side will be J mu, and this side will have to have something which will couple A and phi. Okay. So if we define a potential which is a 4 potential instead of the vector and the scalar potential, a 4 potential A mu like this, okay, which is phi and A. So the zeroth term is phi, the scalar term is phi, zeroth term is the scalar term, and the vector is the A, which has 3, okay, AI, AJ, AK, so 3 X, Y, Z, okay. So if I do this like this, where mu of course goes from 0, 1 to 3, so where the 0 is phi and the 1 to 3 is this vector A. Then with this and this, I can write down these two equations as one single 4 equations. The wave equation now can be read. So now the covariant form of the electromagnetic wave equation in terms of the potential is this. Okay. So we have an A. Okay. So look at over here. There is a double derivative. Okay. So we have to divide it twice. And so it's once divided with respect to alpha, again divided with respect to alpha. Divide means derivative with respect to alpha, again with respect to alpha. There's two derivatives, okay? And your wave equation can be written like this. So to understand how this means is, please go back to the notes that I wrote and see how these two derivatives, how you write down covariant and contravariant derivatives, okay? That is something that you need practice. Without practice, nothing. So some of this we'll probably try to do during the tutorial or maths, but you have to practice. I mean, only way to familiarize you with covariant, contravariant notation is to basically work out problems. Otherwise, you'll always get confused. And once you do it, it becomes very routine. So you exactly know when to do it at the bottom, when to do it at the top. So you know that things comes routine. So this is the covariant TM wave equation in terms of the 4 potential. So this is something that we need. So the Lorentz gauge that I said, which was this divergence of A plus 1 by C del phi del T, that itself becomes like this. Okay, so that can be written in the 4 vector term in terms of this. Okay, so this, look at this and this is basically very similar. Okay. J mu mu is 0. Similarly, the alpha. So this indices, of course, are dummy indices. I could have written J A mu mu equal to 0 also. So that I can write. The fields, once I know the 4 potential, the fields, of course, are obtained as derivatives of the potentials, right? Remember, the fields are derivatives of the potential. In one case, the B is the curl of A. In another case, your phi is connected to your E is connected to your grad phi. Okay. So what would mean that over here, the field must come from the derivative of the 4 potential. Now, to go ahead, one must understand how many components we would need. Okay. So E and B has 6 components. Okay. Let me share this somewhere. Okay. So E and B, as you know, has 6 components. These are 3-dimensional fields. These are vectors, 6 components: Ex, Ey, Ez, and Bx, By, Bz, 6 components. So we need to consider an antisymmetric tensor, a rank 2 antisymmetric tensor which has 6 independent components. Why is rank 2 antisymmetric tensor? Because over here, as you can see, you have to have something which has to be derived twice, have derivative twice. Okay. So you have to have some rank 2 antisymmetric tensor which will have 6 independent components. Somehow we have to define or make one tensor which will be rank 2 and which will be antisymmetric. Okay, so which will basically means your Ex, Ey will have an equivalent of minus Ex minus Ey, your B will have equivalent to minus B. So you have to construct an antisymmetric tensor like that. So the way to construct that is to construct this electromagnetic field tensor by doing it like this. So you define your electromagnetic field F. So your E and B are hidden in this F mu nu. It's a rank 2 antisymmetric tensor. And this by definition is the subtraction of the derivative of the 4 vector potential. So your derivative of the vector potential respect to mu minus derivative of the 4 vector potential respect to nu. That is how you construct this antisymmetric EM field tensor.
Sir.
Okay.
So is there any other deep reason why we consider the second rank tensor?
Can you say it slowly? And
is there any deep reason to define the second rank field strength tensor?
I still can't hear you properly.
I'm saying that is it the only reason why are we considering the second rank tensor?
Why is this the only reason?
He is saying that is it the only reason that we are choosing second rank tensor?
If you do not have a second rank tensor, you will not get a wave equation. If you have not a second, if it's just a 1 rank tensor, you see the wave equation will not work out.
Yeah, for 1 rank it's clear because we need at least 6 components.
And so even with a 3 rank tensor, will not have a wave equation, right? So wave equation is a simple, it's a second degree equation, right? So you don't need a 3 rank tensor, then it will have residues left. It's simple as that, nothing more than that. And of course, the fact that you have to have, see, only with the rank 2 tensors you can have x and y. Only with the rank 2 tensor you can have ex, ey, ez, which will have 3 components of E and 3 components of D. We don't need more than that. So if you have a 3 rank tensor, then you cannot get it. Can you construct a 3 rank tensor with only Ex, Ey, and Ez? What will be the 4th component? So this is the simplest thing that works. Anything else does not satisfy this, and also will not satisfy this. So if it was 3 by, instead of 4 by 4, it was 5 by 5, then it becomes, then you cannot get this structure. Of course, if you are not in 3 dimension, if you are in a different dimension, then you can have different form of this field tensor. And as I said, that your final exam will have you doing some kind of seminar and write up to the seminar, right? So one of the topics of that of the seminar and the write up would be writing EM theories in other than 3 dimensions, higher dimensions. Okay, so one of you or maybe a couple of you will be able to do that and tell what happens over there. Over there you will see this thing will not hold. It will be different. Okay, so let me proceed. So if you write it like this, then of course, as I said, you know B and A, and so then you can write down, as you can see, you can write it down like this. So if you basically work this out, you will find that your F mu nu has this structure. Okay. Now, given F mu nu, you should also have to find what is the Maxwell's equation. Okay. So the first 2 of the Maxwell's equation, which is basically has the charge and the current, this is this 2. You will see this comes out from an equation which is the full covariant form of this equation is F mu nu derived derivative with respect to one of the indices gives you 4 pi by C G mu. Okay. Just to say it again, I think for some of you it's probably as obvious, you have done this before, but quickly see that whenever writing these indices, whichever the index has been contracted, the derivative has been taken, that index goes away, the other remaining index actually remains. Okay. So this is something that you should see. So when you write some index, you must write it like that. So whichever is contracted away, that goes away. The other is, of course, over here is not contracted. Over here is just derivative isn't taken. That goes away. The remaining index becomes the index which is common on both the sides. So that's how you write it consistently. So these 2 Maxwell's equation is written in terms of this equation, this 4 vector form. Okay. Then you go to your conservation of charge. This was your conservation of charge equation. Okay. Okay, this was the conservation of charge equation. So go to your conservation of charge. Okay. You see that if I have this 4 pi C J mu nu, if I take another derivative with respect to mu, that gives you a conservation of charge, that is 0. Then that means F mu nu, we have twice taking the derivative of F mu nu, one with respect to mu and one with respect to nu. So that will be equal to 0. Okay. So this is 0. And this basically shows you that one can play around with the indices over here. And that tells you that this F mu nu has to have this kind of structure where F mu nu. So remember, this is equal to 0. So one can add this plus this to be equal to 0. So look at this plus this will be equal to 0. And this is antisymmetric. So use the properties of antisymmetry. Okay. And so from here, you come to this independently, that F mu nu has this kind of property where if I interchange one of the index, okay. So over here, mu nu has been interchanged to nu mu, and you get a minus sign. Okay. So come to this kind of thing. So this is what you want. The other two Maxwell's equation other than this are these two Maxwell's equation, and this is slightly complicated, okay, but one can show that these two equations can be written in terms of another equation which involves the derivative of the F mu nu. Okay, where is the F mu nu of the field tensor? So you have the cyclic derivative of the field tensor. Okay, you have this kind of thing which gives you this equation. So cyclic, so mu, nu, and sigma, that goes away like this. Sometimes it is written in a concise notation. So this is how you write it in a concise notation. So this box over here means permutation of the indices. Okay. So even permutation gives you a positive sign, and odd permutation gives you a negative sign. So you basically, some of those books will write it, instead of writing it in this full form, will write it like this. Again, you have to go to your tensor notations that I wrote in the previous class, or I mean basically uploaded. Over there, you will find this is written. So to give an example, if it was A alpha beta, okay, so this basically means this. So this is a concise way of writing A alpha beta minus A beta alpha. Okay, this is how I write it. So in the same way, F mu nu is equal to A mu nu, right? So because this basically is, if I change my alpha beta to mu nu, this is nothing but F mu nu, right? So look over here. This was the definition. So I could have written this in terms of a box. This A mu nu minus A mu nu, I could have written it like this. I could have written it like this. Okay. So that's the shorthand definition. You'll get used to this when you see again and again. Also, this is something that is a property of the tensor, because you know this F mu nu is a second rank tensor. So its Lorentz transformation will be like this. So you have so lambda is the Lorentz transform written in terms of a matrix. Okay. So your F mu nu, you need two of these lambdas. Okay. So take an F alpha beta, you have a lambda mu beta over here, you have another lambda mu alpha over here, that gives you a F mu nu in the prime frame. So you have to transform it because there are two sets of indices over here. You have to use Lorentz transformation twice. So this will be a part of your homework. You basically try to use these equations over here. So I actually write down the equation 210 and 201. Which is 210? Let's see. This is 210. This Lorentz transformation equation, and 201 is this equation. this field tensor equation. We basically use these two equations to show that your electric field and your magnetic field have this kind of transformation properties. Okay. The next thing that you need to know is basically what happens to quantities formed by joining F mu nu's together. So I can have a completely covariant F mu nu with a completely contravariant F mu nu, okay, to get a something which is, so this mu nu's will contact with each other, okay, to get something like this, which is invariant under Lorentz transformation. So this is very important, this formula. So F mu nu times F mu nu, this gives you B squared minus E squared. And this, you should know what was it. Remember, it has something to do with the energy. Similarly, this determinant of F mu nu gives you E dot B squared. This is also invariant. So we can get two invariants, two Lorentz invariant by suitably manipulating my F mu nu. So, by the way, I basically have written it because determinant of second rank tensor is basically a scalar. That's why you get this. This also, if you look at the conservation laws of ED, these are related to things which are conserved in ED. Okay. We also need to connect the EM theory with mechanics. Okay. So Maxwell's equations are covariant, that we have already shown right now. Newton's equations are not covariant. Okay, they obey Galilean invariance. Okay. So the idea is we need to cast these dynamic equations in covariant tensor form, so that we can use Newton's equation along with Maxwell's equation. Because ultimately we want to, remember, we want to go back and do Lagrangians. We want to go back to where there is particle part also there. Okay. So there is a field part and there's a particle part. The field part will automatically become covariant because this comes from Maxwell's equation. The particle part, we want to write that down also in a manifestly covariant form. So we have to basically cast the dynamical equations in covariant tensor forms. The first thing, just like the Q over here, M0 is a particle rest mass, that is scalar. Okay, that does not change. And it can be defined in invariant manner. So you can go from a particle where that is at rest, measure it, and then go to another frame, and the mass of that particle, if it is at rest, will simply the same. Unless you have looked up the previous day's notes, you will not know this, but it was there. The force momentum is defined exactly the same way you define a momentum. So mass into velocity is momentum. So mass, which is the particle rest mass, into its force velocity is your force momentum. Exactly the same definition. Okay. So in the relativistic limit, this will become just V and this will become P. Okay. So it will become M0V. We can try to expand this thing P0C in terms of V less than C. Okay. So if you do that, P0 is basically M0 U0, right? This is P0, then this will be U0. So M0 U0 is P0. So P0C is M0C, the zeroth component of the, into the zeroth component of the force velocity. And this is basically equal to this, because I know what is the zeroth component of force velocity from the previous notes. Okay. So there will be a C over here, and so it will M0C squared times 1 minus B squared plus C squared. Now if I again expand this, then you see that this P0C is basically this first part, which is the rest mass m0 c squared plus the kinetic energy, which is m0 v squared, and then you can have higher. So therefore, we can interpret this thing, this energy P0 c, as the total energy of the particle. Okay, and what I can do is I can write down the relativistic expression of the spatial momentum. So your spatial momentum again was m0v times gamma, because v transforms as gamma v. So your spatial momentum is P is gamma times m0v. I could have taken the m0v on this side. Okay. So then what I can do is that I can add this spatial momentum with the zeroth component, which is P0c, to write down my 4 momentum over here. Okay. So your 4 momentum then becomes E by C and your 3 momentum. This is how your 4 momentum becomes. So you can, now we have a way of defining my 4 momentum in terms of the energy and the 3 momentum. Okay. So once you can define the 4 momentum, you can write down force laws very easily, because the rate of change of momentum is force. Okay. So that's why we need to write it like this. So in one of your homework, you had to show, so again, if you have seen the notes, you have to show that you get this something which is invariant made of this product of the 4 velocities. So if you take a product of 4 velocities, you get minus c squared, and that's our invariant, obviously, right? So you can show using this that your E squared is your m0 c4 plus c squared p squared. These are the equations that you have learned very well. Basically, this sort of reduces to E is equal to mc squared equation. Okay, so this is the equation that. So your total energy is in terms of your rest mass energy squared plus your c squared p squared, where p is your 3 momentum. Okay. Now, since photons are of course massless, has velocity, so the 4 momentum cannot be defined in terms of this. It's something that, okay. However, we still define 4 momentum like this. So your 4 momentum cannot be defined in terms of m0 u to the power mu. So u mu like this, we cannot define a 4 momentum, but we can still define a 4 momentum like this. Okay. So in this case, your E is equal to h cross omega and your P is equal to h cross k. So you cannot still, so it still doesn't have, the photon still doesn't have a rest mass, but its 4 momentum can still be defined in terms of the energy and its momentum. So momentum comes in terms of h cross k, energy comes in terms of h cross omega. That's very interesting actually. In this case, of course, your k mu is this. This is something that we I mentioned in the last class. It came from the definition of the wave, and we had this k, the 4 vector k, which in terms of the 3 vector k and the frequency of it. Okay. So for the photon, we basically have my 4 momentum p nu as h cross k mu. Okay. So the first component is the energy, the second component is the momentum. And of course, you can show that your p squared is 0, your E is equal to c times p. So these things you can quickly show. Once we know momentum, once you know the 4 velocities, we can also write down the 4 acceleration. Again, this is exactly done the same way as classical mechanics, except over here, the derivative is respect to something which is an invariant. So your A mu is a derivative of the 4 velocity with respect to tau and not t. Okay, it's respect to the proper time. So you define your 4 acceleration. This is definition by the way. So whenever I have these 3 lines, it's basically this is how I define it. So over here, I define my 4 acceleration as the derivative of the 4 velocity with respect to the proper time tau. Remember, d tau was an invariant. Okay. So one interesting upshot of this is that if I define it like this, in relativity, you see that this 4 acceleration and 4 velocities are orthogonal to each other. Okay, this is not there in Galilean. So it's not necessary that your acceleration is always orthogonal to your velocity. You can accelerate in the same direction as your velocity. That's with 3 velocities and 3 acceleration. But in special theory, because of the way it's defined, you can show that this 4 acceleration and 4 velocities are orthogonal. Okay, because of this thing. Where is it? C squared. Because of this relation, that you can get an invariant c squared out of the 4 velocities. So because this thing holds that you can get an invariant of c squared because of the 4 velocities, you can basically dot product the acceleration and the velocity, and you will see that you will come up with dd tau of minus c squared. C squared is invariant, so it's 0. So basically your 4 acceleration and 4 velocities are orthogonal to each other in when you do it with 4 components. Okay. When you have both also the energy and the momentum together. Okay. So that's a thing, and that's used a lot actually in many applications. We use this property. As I mentioned before, the force is basically written in terms of mass into acceleration, or the rate of change of the momentum. But again, the rate is basically in terms of dd tau, not ddt. Okay, so this is how I define. And so if I define my force like this, then my F mu nu is dp mu d tau. Okay. Remember, in EM theory, your force, the Lorentz force, has this form. So I can write down this itself in terms of the, so over here, this F will become F mu nu. And this side, you have to write down something which will come in terms of the field tensor. Okay. So this side has to be a field tensor, and this side will be your Lorentz force in terms of F mu. F mu. So this F and the field tensor F's are different. Okay. So this is how I can write down. So you can write down the force as Q by C. These are the 2 scalars. F mu nu E nu. So you see that if I convert this 4 form into the energy and the 3 spatial form, that will basically, this will basically divide into this part and this part. So here is a homework for you, which basically shows that from the definition of Lorentz force and the 4 force, the equation of motion of a charged particle is this. So don't use this. Okay? Don't use this. That F mu is m0 mu. So show that. Okay. Show that its mu is equal to 0 component gives us the conservation of energy. So this is a question. This is your homework. So if you take the mu equal to 0 component, show that it will give you the conservation of energy. Also, because of the fact that your 4 acceleration is orthogonal to 4 velocity, it turns out that your 4 force is also orthogonal to 4 velocity. So if I basically dot product my Lorentz force, the 4 Lorentz force with the 4 velocity, you will get basically this thing, and this will become 0. So this is orthogonal to it. So you can basically show that this is antisymmetric, this is antisymmetric, and this is symmetric. So this term will become basically 0. Because we'll have one more term over there, then you can bring both the term on one side and that will become 0. So basically with this kind of material, what we can do, that we can basically go ahead and do everything that we want to do for the rest of the course. We can write down full equations in full covariant ED. We can do covariant formulation when we do charged particles and radiation by charged particles and things like that whenever we want to. Okay, it's not always that we'll use it. is just something that sometimes is handy, sometimes it's not so handy. I mean, it's not always that if you can write down something very simply, it is always handy. And it turns out that you will very easily write down Maxwell's equation from this. So one of the homework probably is to write down your Maxwell's equation in terms of your F mu nu. Okay. So you will see that 4 Maxwell's equations are written very simply in terms of F mu nu. It's not necessary that it is always handy or it shows you all the physics. So one of the reasons that I did the full Lagrangian and worked out the Maxwell's equation, because over there the physics comes out much more clearly than when everything is written in terms of a. It's quite nice that you can write down all the Maxwell's equation in terms of a very small equation, but it does not tell you all the physics that goes inside. It does not show you what are the source equations, it does not show you what are the constant equations, which is why we did actually the actual Lagrangian to show how the actual Lagrangian and how its action and how the minimization of action from the actual Lagrangian. That's why you actually spend so much of time. After this, when you write it in this way, doing the action is very simple. So one of the homework would be probably to do the action with this kind of Lagrangian. So write down the Lagrangian over here for F mu nu and find out how to say action. Okay. So I will give that as a homework. I will give you hints. I will give it as a homework. And then you guys will have to do that. What is more interesting actually is to do the reverse. So you go to the Lagrangian space, you write down the Lagrangian, okay, which we have been now, all of you are expert in doing it. Write down action like Lagrangian. And over there, show that the existence of those Lagrangians, okay, itself tells you that, hold on, I cannot minimize stuff. I can't see anyway. Can you still see the thing? Can you still see the shared thing?
Yes, sir. Okay.
And what do you see? Hold on. You see my cursor and stuff?
Yeah. Okay.
So something that you will see in the next day is basically, and that will be more interesting for me because that has much more physics in it other than this mathematical things that we did over here. Was just playing with the tensor form of equations, you know, is to show that if you write down your electromagnetic Lagrangians over there, you know, one can look at what are the properties of the conserved quantities, and from the conserved quantities, remember certain things that we did, how things become conserved, how you write down the G, in the endpoint variations, how from those kind of stuff, one can actually write down many of the equations that we did today. So you can write down that things have to be, you know, covariant. Things have to have this Lorentz covariance in it. The relations between P and E, this will have to have certain form. All these things will come out of, you know, doing Hamiltonian mechanics. So we'll basically do Hamiltonian mechanics of EM fields, and from there we will derive most of these equations that we did. And those are much more intuitive to understand. I feel it's quite also interesting and not generally shown in most books. Okay, so we'll do that next day. I will not show you, not scroll through the screen. I will work it out next day because I don't want to scroll through the screen. Okay, and this stuff I find out to be, you know, things that you have done before, most of it. So I don't want to spend more time over here, but we'll come back to things that hopefully most of you have not done. And then we'll again start writing. In the meantime, you find out a time when we can do some problems. So we'll start doing some problems on special theory, so that you get used to working with indices, working with some concepts and stuff like that. Okay. And remember this Sunday, I mean Monday morning, 6 a.m. you have the deadline for your homework assignments. Okay. I think only one person has submitted the homework, but all the rest you have to submit the homework. So please do not delay in submitting the homework, because the next homework will be on special theory and these things that we do till the next class. Okay, so please submit your homework.
But the time is not updated on the model, I think.
What?
Time is not updated on the model.
So in the model, I think the deadline was till
Show 6
9.
hours.
Yeah, I will extend the deadline till Monday morning. Thanks for reminding.
It was Monday evening.
Hey, 6 a.m. Monday.
6 p.m. sir, you wrote.
Yesterday.
Yes, sir.
Last class,
6
sir.
a.m. Yeah, last time you wrote.
I remember definitely, sir. It was PM, sir.
Oh,
Yes,
come
I
on.
also remember.
Come on, you guys. Okay, I will do it because it was my mistake. I will do it till 6 p.m. But it was intended to be 6 a.m. I wanted to give you 2 days, but not like 6 p.m. Monday. But thanks for reminding me. I will extend the deadline in Monday. Okay. So that's why we'll stop today. Next day we'll actually again start with the Blackboard writing, and we'll continue with stuff that will be hopefully really more interesting than what we did in the last 2 classes. Okay. So we'll stop over here. So that's the basic of all that I wanted to do about the standard special theory of relativity that is part of the course. I'm not going to do more about this. We'll go back to EM theory and do much more details of EM theory. So there will be a lot more EM theory coming after this. Okay, see you on Wednesday then. And please submit your homework by time.
Sir,
Yes, Nikhil?
can you tell slightly more about the Bianchi identity in this case? By the way, you don't mention it, Bianchi identity.
Bianchi identities, okay. Maybe during the what do you call the homework, the class, when we'll work it out at that time, we can do that. Okay. Bianchi identities are needed more in GR, not over here. Okay.
Yeah, that is fine, but it's a geometrical property, right?
Yes. So we will do. So during the tutorial, let us do Bianchi identities then. I'll put in something on Bianchi identities in the tutorial.
Okay, sir.
I will keep a note of this Bianchi identities. Okay. Okay, we can stop now. Stop share. Yeah, I can stop recording.